In this video, we are going to discuss on tutorial 20. So the topic is heat capacities. So the first question, 3 moles of an ideal gas at 480 Kelvin are compressed until the pressure doubles. Find the work done on the gas. So R is given 8.31 joule per mole per Kelvin. Okay, number of moles given 3. And then temperature 480, and pressure doubles mean let's say the initial pressure is P1, so doubles become 2 P1. And finally find the work done. Okay, so R is given, so that's mean the formula we use is work done equals to integration P with respect to V. So the changes of volume is from V1 to V2. So the pressure we use PV equals to nRT. So we factor out nRT. So bracket here is 1 over V. So that's mean the integration 1 over V with respect to V will give you ln. Ln. And RT is constant. So ln V2 over V1 because you substitute V2 and V1. So ln V2 minus V1. The minus, we use log rule. So we convert it to V2 over V1. Okay, so you can refer to the derivation of the formula work done for the constant temperature here, constant temperature. So pressure change and volume change. Okay, so in this case temperature constant 480 Kelvin. Okay, so we use this formula for work done. Okay, now for work for V2 over V1, because temperature is constant, so V2 over V1 will be equals to the P1 over P2. From here also we can see PV equals to nRT, so nRT is constant. So instead of substituting V1 over V2 over V1, so we can substitute P1 over P2. Okay, because they are inversely to each other. Okay, so now V2 over V1 is equals to P1 over P2. Okay, so from here, then you substitute all the values into the equation. So the P1, let it be P1. So the P2 pressure is double. So you write as 2P1. So cancel the P1 and multiply this 3. So you get negative 8,294 joule. Okay, so that's the answer. Next, we do question 2. An ideal gas undergoes expansion from 75 centimeter cube to 120 centimeter cube at constant pressure, 1,100 Newton per meter squared. So the initial temperature of the gas is 24 degrees Celsius. Calculate the final temperature of the gas and the work done by the gas during expansion. Okay, so you are given volume 1 and volume 2. And this is pressure constant and temperature T1, and we are going to find the final temperature T2. Okay, so question A, we can use V1 over T1 equals to V2 over T2. Okay? Or you can use PV equals to nRT. PV equals to nRT, and you form two equations. Then you use ratio. Let's say we use this one, V1 over T1 equals to V2 over T2. So you substitute 75, temperature convert to Kelvin. Okay, then 120 is the volume. And we are going to find temperature 2. So the answer is 475 Kelvin. Okay, question B, work done by the gas during expansion. So for the work done, we use P delta V because pressure is constant. So you can use this formula of work done. So P times change in volume. So pressure is constant 1100 and the change in temperature volume is 120 minus 75. Don't forget convert to meter cube. So times 10 to the power of negative 6. So the answer is 20.0 joule. Okay, so done for question 2. Okay, question 3. A gas in a cylinder is held at a constant pressure of 1.15 times 10 to the 5 Pascal. So it is cooled and compressed from 2.16 meter cube to 1.61 meter cube. The internal energy of the gas decreases by 1.10 times 10 to the power of 5 joule. So find the work done on the gas and calculate the value of heat flow and state its direction. Okay, so the question give pressure, volume 1 and volume 2, and then internal energy, so this is decreases, so that's mean is negative. Okay, the sign is negative. So we are going to find the work done. So the formula, because of the pressure constant, so we use this formula, work equals to P times change in volume. So pressure 1.15 times 10 to the power of 5. So the volume change from final minus initial, so 1.61 minus 2.16. And the answer we got negative because this is the work done on the gas. So work done on the gas, the sign is negative. Okay, for B question, calculate the value of heat flow and state its direction. So the heat flow we use first law of thermodynamic. So delta Q equals to delta U plus work done. Okay? So the delta U or change in internal energy negative because decreases. So negative 1.10 times 10 to the power of 5 plus. So the work done on the gas is negative. And total these two, so we get negative 1.73 times 10 to the power of 5 joule. So what does this mean, negative? So negative means the heat flow out from the gas. Okay, so this is the direction of the heat flow. Okay, next we go to question 4. A 5 kilogram material X has a heat capacity of 1018 joule per Kelvin. Calculate the specific heat capacity for the material. So you are given mass, you are given heat capacity, and we are going to find specific heat capacity. So specific heat capacity, we use small letter C, and heat capacity is capital letter C. So the specific heat capacity is the joule per, the unit is joule per Kelvin per kilogram. So we divide, the formula will be C divided by M, because per the unit, from the unit we know that is per, we add one more unit per kilogram here. So the formula will be specific heat capacity equals to the heat capacity over mass. Okay, so heat capacity is 1018 divided by mass 5 kg. So the answer for specific heat capacity is 2003.6 joule per kilogram per Kelvin. Okay, for B, to find the relative molecular mass, so you are given the relative molecular mass. So this 140 is the molar mass. Okay, so we are going to find molar heat capacity. So for molar heat capacity, the formula is C over N. So the unit will be joule per Kelvin per mole, or joule per mole per Kelvin. So that's why the heat capacity we divide by number of moles. Okay, so for number of moles, we use mass over molar mass. That's why molar mass is given. So the heat capacity, so to find the molar heat capacity, so we bring the molar mass on the top, so we get mc over m, mass of the gas. Then substitute molar mass and heat capacity, and then the mass 5 kg, so you get the answer molar heat capacity 28.504 joule per mole per Kelvin. Okay, next question C. Determine the change in temperature if 0.15 kg is given. So this is the new mass. Okay, we label as M prime. So losses 860 joule of heat. So that's mean this is delta Q, and from the word losses here, that's mean is negative. The symbol or the sign we give to heat here is negative. Okay, so we use formula delta Q equals to MC delta theta. So delta Q is negative 860. So the mass 0.15. C is 203.6. We calculate in A already. So we substitute this A because this C is a specific heat capacity. And then the delta theta is what is the question one is delta theta. Okay, so we get negative 28.16 degrees Celsius. Okay, so that's the answer. Okay, so next we go to question 5. Okay, question 5. The PV graph below shows the expansion of a gas through two stages, KL and LM. KL and LM. So look at the arrow given here. So the work done by the gas is 1.125 joule. So find the value of X. So X is not given. From the reading for in the X-axis here, X not given. So the work done by the gas, so the work here is positive because done by the gas. And the value X is what we're going to find. So because you are given PV graph, so area under the graph is equals to the work done. And we divide into 2, so the work done by KL plus the work done by the LM here, LM. Okay, so area we divide into 2, area of trapezium 1 and trapezium 2, and the total of work done is given 1.125, and it is positive, and by the gas, so it is positive. Okay, so area of the trapezium half times the two parallel line here is 70 and plus 40, the two parallel line of the trapezium, and then the volume or the distance here, x minus 0.01, x minus 0.15. Okay, then plus area under LM graph. So the two parallel lines here is 20 plus 50, okay, 40, 20 plus 40, and then the height of this trapezium will be 0.040 minus x. So you can solve for x, expand the bracket here, and then the answer is x equals to 0.03 meter. So I didn't put meter cube volume, so I didn't put the unit there. So you must put the unit 0.03 meter cube. Okay, next we do question 6. Question 5. The heat of vaporization of water boiling at temperature 120 degrees Celsius and pressure to atmosphere is 2.20 times 10 to the power of 6 joule per kilogram. So this is heat of vaporization. Okay, so for this temperature and for this pressure, this is L. Okay, heat of vaporization. So we use symbol L. So at the pressure of 2 atmosphere, 1 kilogram of water with a volume 1 times 10 to the power of negative 3 meter cube changes to 1 kilogram of steam. So the mass is constant, 1 kilogram. That's why this is heat of vaporization. Okay, so pressure 2 atmosphere, so the M 1 kilogram, and the volume V1 and V2 given, the volume change. Okay, calculate the amount of work done to overcome the pressure and calculate the change in internal energy. So for the work done, okay, so and 1 atmosphere is given equals to 1.013 times 10 to the power of 5 Pascal. So we need to convert to SI unit. So work done, we can use P delta V because P is constant, 2 atmosphere. So convert to atmosphere to Pascal. And then the volume change is final minus initial. So V2 minus V1, 0.825 minus 1 times 10 to the power negative 3. Okay, so this one. And the answer is 1.67 times 10 to the power 5 joule. So this is positive work. Positive work. So work done. Positive. We got positive. Then for B, another why positive, because here the volume increases. The volume increases, so this is expansion, so you should get positive value. Okay, for B, change in internal energy, delta U symbol. So to find delta U, so you need to find heat first, because we are going to use first law of thermodynamic. So we need to find heat. So the heat we can use ml. L is heat of vaporization. So mass is 1 kilogram. So we get answer 2.20 times 10 to the power 6 joule. So this is the heat, and this is positive, because the heat is because at this temperature 20 degrees Celsius, so the heat is absorbed for the water to boil and become steam. So heat is absorbed, so that means delta Q is positive. So delta, we change the position here. Delta U equals to delta Q minus work. So delta Q is 2.20 times 10 to the power 6, and it is positive. And then minus the work done. The work done also positive. And you get the answer delta U is positive. So that means the internal energy is increases. Internal energy increase because you got positive value 2.033 times 10 to the power of 6 joule. So the internal energy increases. Okay, so that's all for tutorial 20. Bye bye.